ladies and gentlemen. We're going to be talking about Hess's law tonight. Hess's law is located in 5.6 in your white textbook, and we'll define Hess's law as if we have a reaction that's carried out in a series of steps, meaning there's often maybe 2, 3, 4, or 5 different reactions um, that are forming one final product. The delta H value, that change in heat or change in heat at a constant pressure, which we call enthalpy, is the sum of the delta H from each step. So let me give you an example of what we're talking about here. If we were to take, let's say, methane gas, which is CH4, and we were to react it with a couple oxygen, we're going to make this actually oxygen gas, we know that it's going to react to form carbon dioxide plus water. And we could look up or find a delta H value for this. As delta H is going to be negative 802 kilojoules. Now, also, if we were looking at, let's say, taking the water, H2O, from a gas to a liquid, that itself, in order to go from a gas to a liquid, you have to remove heat. And so we'd have to remove about 88 kilojoules of heat. And we could say that these are two steps that we could sum. And what we would do is when we sum up these two steps, we're looking for anything that we can cancel out. Anything that is the same on one side of the arrow and the other, meaning we have to have the same reactant and product that we could cancel out. And so what we're going to look for is, do we have any reactants and products that are the same state of matter and the same chemical species, and we can cancel those out. And so hopefully you can see that we have H2O gas here, and we have 2 of those, so we'd cancel those out, and we have 2 H2O gas here. Now if we only had 1 H2O, and let's say in this product up here, and we had 2 down here, we would just cancel out the 2 and make that a 1, and we would leave that H2O down here. But we have a 2 to 2, so we can cancel that out. Now what we can do is we can rewrite this equation as CH4 plus 2O2 yielding CO2 plus 2H2O, and what's left is the liquid. Now, to get our overall delta H value, what we're going to do is we're going to take the sum of this and this, those enthalpy values of negative 802 plus, we're going to take negative 88, and we're going to add those together, and so we get negative 890 kilojoules. So this is a real simple example of what we're talking about in Hess's law, where we take 2 equations, 1, 2, and we sum them up here. Now, before we get into summing up these equations, we need to talk about how we manipulate these equations. And there's a couple different ways we can manipulate these equations, and we sometimes have to manipulate equations just so that we can make our reaction come out how we want it to come out. We'll talk more about that in a minute. So let's say like we're using the same reaction, we said multiply by a coefficient. So if we have 2 moles or 2 molecules of gaseous water here, and we're forming 2 moles or 2 molecules of liquid water, we would have negative 88 kilojoules. Now, if we went through and we multiplied a coefficient, let's say we wanted 4 moles, so let's say we multiplied this entire expression by 2, so that we got 4, that is a 2 right there, so we get 4 H2O gas goes to 4 H2O liquid. What we would have to do is on our delta H value, we'd have to take negative 88, and we'd have to multiply that guy by 2 kilojoules, by 2, and to get our new value. I believe that comes out to negative 176 kilojoules there. So we sometimes have to do this in Hess's loss problems, and we'll show you some examples of this. Also, we occasionally will have to reverse reactions, just again to get things the way we want them, and that'll make more sense once we do an application down here. So let's say we have this this reaction again where we have gaseous going to liquid. This is a condensation type deal. And let's say we wanted to reverse this reaction, so we had 2H2O liquid going to 2H2O gas. What's going to happen is we're going to have to change the sign, and because the sign here is negative, we're going to make the sign positive here. It doesn't affect the the value, we just change the sign just like that. So we occasionally have to do that by flipping reactions or multiplying through a coefficient. And so let's get down here and let's talk about an application of Hess's law and how we deal with this. So what's happening here is we're given two reactions, this reaction here and this reaction here, and these two reactions are we need to manipulate them or maybe not manipulate them so that we end up with this final reaction that's right down here, which is carbon solid plus a half a mole of oxygen yields carbon monoxide. That's what we're ultimately trying to end up and get to. And we need to figure out how we're going to manipulate these equations to get to that. So, and cancel some stuff out too. So let's go back up here and look. And because I see carbon solid here, and in number 3 here I see carbon solid here, that leads me to believe that I'm not going to need to flip that reaction. I'm just going to leave it as is right now. Looking over here, I've got on number 4, I've got carbon monoxide gas listed as a reactant, but down here I have carbon monoxide gas listed as a product, and I want carbon monoxide gas as a product. So what I'm going to do is I'm going to take the second reaction, which was numbered number 4, and I'm going to flip it. So I'm going to put carbon dioxide gas yields carbon monoxide gas plus a half of an oxygen gas. And because I flip it, delta H is going to equal to a positive 283.3 kilojoules. And I think that we'll cross this one out just to make sure that we don't reuse that one. Now, what I want to do is see if I can cancel anything out. Not cross cancel, I'm sorry, just cancel anything out. And remember, anything that exists on the product side and exactly on the reactant side we can cross out. Kind of like when we were doing net ionic equations, we crossed those guys out. So I crossed out the CO2. It exists on both sides, which is good because I didn't want the CO2 down here in my final equation anyway. Anything else I can cancel out? I've got oxygen here. I've got a mole of oxygen, and here I've got a half a mole of oxygen. So what I can do is I can cancel out the half a mole here and turn this guy into a half a mole there, basically subtracting off a half a mole from one. Now we're looking good. We've got carbon solid, and we've got carbon solid down here. We've got a half oxygen there, and we've got CO there. I think we're done with what we need to be done. And so what we're just going to do now is we're going to go ahead and take the sum of those two reactions. So it's going to be negative 393.5 kilojoules, and we're going to add that value to 283.3 kilojoules. And we're probably going to get, it looks like a negative value because that 393 is larger. And I believe if my math is right, it comes out to negative 110.5 kilojoules. So that's going to be our delta H value for the sum of these two types of reactions. Let's give you one more problem, see what we can do with this one. So this one says calculate, it looks like a similar equation here. We're going to calculate delta H for two carbons reacting with a mole of hydrogen to produce C2H2 gas, and we're given three separate equations here to work with. So what we need to do is on these three separate given equations, we need to manipulate them so it ends up as this equation as our final equation here. So let's do that. Let me kind of just erase this stuff off here, and let's do this. So I'm looking at the first one here, and I have C2H2 as a reactant, but I have C2H2 as a product here. Leads me to believe I'm probably going to want to flip reaction number 1. So let's go ahead and flip that guy. So I get 2CO, 2 gas plus H2O liquid yields C2H2 gas plus 5/2 O2. Not a big fan of fractions, so I'm going to get rid of that. Changing the sign here, positive 1299.6 kilojoules. And let's hope that works. Then looking down here, I've got one carbon, but I've got two carbons, and I don't see carbon solid existing anywhere else. Up here I have two of them, So that leads me to believe I might need to multiply this entire expression by 2. So let's go ahead and do that. 2 carbon solids plus 2 oxygen gases yields 2 carbon dioxide gases. And so our delta H value is going to increase in a negative portion. And so it's going to be 2 multiplied by negative 393.5 kilojoules. Okay. And then let's look down here at our next one. And I have H2 as a reactant, and up in my original I have H2 as a reactant. So first off, that leads me to believe I don't want to flip this equation. I also have water listed here, and I don't see water in my original equation at all up here. There's no water in it. So that means I'm going to try to make sure water cancels out. And glancing at the first one, we have water here, water there. So I think this might be good. 1H2, 1H2. So I think we're now okay. Now I'm going to go back up here. I'm going to do something really quickly just to make life easier on myself. And like I said before, I don't really care for fractions right here. And so I'm going to go ahead and divide that fraction out and make it a decimal. And 5/2 comes out to be 2.5 moles there. That just makes life easier on me. Down here on this oxygen, and in the very third one, this should be number 3, by the way. I'm going to make this a 0.5. A half is the same thing. Now let's see if we can cancel some stuff out here. So we've got 2 CO2s on a reactant side here. I'm going to cancel that with 2 CO2s there. I've got 1 water there. I'm going to cancel with 1 water there. I have a carbon. We're going to leave that carbon alone. Oh, I'm sorry, I'm looking on the wrong one. Let's get rid of that guy. Let's look at this guy down here. I have 2 carbons. Okay, now let's deal with some oxygens here. So here I have 2 oxygens, plus I have another half of an oxygen here, so that's 2.5 oxygens on the reactant side, and over here I have 2.5 oxygens on the product side. I can cancel that guy out. And so I think I might be good. Let's see here. I'm going to just start writing some stuff down here. So here I see 2 carbon solids, 2 carbon solids, and then here I see 1 mole of hydrogen, 1 H2 gas, and then let's see over here I see C2H2, just one of those guys, and let me double check that is the same as what I originally wanted. So I am now ready to take my sum. So let's see, we have from the first one we have 1299.6 kilojoules, and we're going to add this to our second one, which is going to be 2 multiplied by negative 393.5 kilojoules, and on my third one I didn't look like I gave us a delta H value there, and I should have. It looks like it's a quick little typo. I'm just going to go ahead and fill it back in. This delta H would be actually given to us. It's in my notes. I've got it as negative 285.8 kilojoules there. So, and I did not manipulate. Did I manipulate that equation? I did not manipulate that equation at all. So I'm just going to use it. Negative 285.8 kilojoules. And so I'm going to take the sum of those guys. And I believe if this comes out correctly, it should be 226.8 kilojoules. And there we go. And that's how we do Hess's law problems. There will be a homework assignment that goes along with tonight's lecture. Hope you have a good night.